Rudewright Academy. Learn it, teach it, remember it. So here's the idea that changes the game, the sliding window. By the end of this, you won't just memorize it. You'll see the pattern before you finish reading the code. Picture a train window. As the train rolls forward, new scenery slides in on one edge and old scenery slides out the other. You never turn around and rescan the whole world. The view updates. It never restarts. That window is our whole idea. It's a contiguous slice of a sequence with a left edge and a right edge that moves along the data. One thing enters on the right. One thing leaves on the left. Here's a row of numbers. Find the largest sum of any three in a row. The first block, 2, 1, 5, adds to 8. The obvious way re-adds every block from scratch. For 1,000,000 numbers and a block of 1,000, that's close to 1,000,000,000 additions. That's block size times the number of positions. But look closer. Between one block and the next, almost nothing changed. The 1 and the 5 are in both, and we re-added them for nothing. We threw away a good sum and rebuilt it, losing one number and gaining one. So don't rebuild it, carry it. Take the old sum, subtract the number that left, and add the number that entered. That's two operations, whatever the block size. Pay the full cost once for the first block. Then slide. Subtract the left, add the right, and check the best. 8, then 7, 9, the best so far, then 6. The answer is 9. In code, you build the first window sum. Then you sweep the right edge, each step adding what enters and subtracting what left, keeping the best. Count the work. The slow way is block size times positions, 1,000,000,000. The window pays the full cost once, then two operations a step, 1,000,000. We replaced rescanning with updating. Now the harder, richer flavor. Find the longest stretch with no repeated letter. You can't fix the width because finding the right width is the problem. The window has to breathe, growing when it can, shrinking when it must. Here is the single most important idea. A variable window is governed by a property it must always keep true. It's invariant. Here, the window contains no repeated letter. The left edge contracts only to restore the promise. The right edge expands, greedy, always reaching. So the loop has a heartbeat. Grow on the right. If that broke the promise, shrink from the left until it holds again. Then record how good the valid window is. A little count is the window's memory. Trace it, one letter at a time. A enters, no repeat. Length 1. B enters, valid, length 2. C enters, valid, length 3, the best so far. A again, but an A is already inside, so the promise breaks. Shrink from the left, drop the old A, and we're valid again. B repeats, so shrink and drop the B. C repeats, so shrink and drop the C. B repeats, drop the A, still a repeat, drop the B too, length 2. B again, shrink twice more, length 1. The longest valid window we ever saw was 3, and we found it in a single left-to-right pass. Why is it fast? Watch only the pointers. The right edge crossed the sequence once. The left edge crossed once. Add them, and that's at most twice the number of elements. Each move does a constant bit of work, so the whole thing is linear. It looks like a nested loop, and nested usually means the work multiplies. But the left edge never rewinds. It picks up where it left off and crawls forward once across the whole run. That's shared progress, not repeated work. Linear and not quadratic. A sister problem flips the feeling. Given a string and a set of required letters, find the shortest stretch that contains all of them. The shape is identical, but the invariant and the goal trade places. There, valid meant no repeat, and we wanted the longest. Here, valid means it contains everything required, and we want the shortest. So grow the right edge until the window first contains all of A, B, and C. The moment it's valid, don't stop. Squeeze the left as far as it stays valid because a smaller valid window is a better answer. Record the tightest, then grow again. The best shrinks to 4, B, A, N, C. Every sliding window is the same 5 decisions. 1. Fixed or variable. 2. Name the invariant in plain English. 3. The bookkeeping that makes it cheap to check. 4. Which edge moves when. 5. When you record the answer. Get the invariant right and the rest falls out. How do you spot one? Ask 4 things. Is the answer a contiguous stretch? A best or a count over those stretches? Can you update cheaply as the right edge moves? And is there a one-directional relationship to lean on? 4 yeses, and it's a window. That last condition is the quiet one. When the window grows, does the quantity you track move in one direction, a sum that only climbs with all positive numbers? Then the left never has to back up. But let negatives in and the sum swings both ways and the simple window breaks. 4 traps cause most broken window code. 1. Recording in the wrong place, so measure a valid window, never a broken one. 2. Forgetting to unregister what leaves, because every grow needs a mirror ungrow. 3. Moving the left edge too far when it should only advance, only just enough. 4. Applying it where the monotonic condition fails. The universal fix is to trace the 2 pointers by hand on a tiny input. Print the window and your bookkeeping at every step. Then find the first row where the printed window disagrees with what you claim. That's the broken update. Almost every window wears one of 2 outfits. Fixed, where the size is given, 1 running summary, and you slide. Variable, where the size is the unknown, 2 independent edges. You grow and shrink on a break for a longest window, or grow then squeeze for a shortest one. Master it by stating the invariant out loud on a ladder of problems. Max sum of a block, longest with no repeats, at most k distinct, smallest subarray over a target, minimum window cover until you see the invariant before you finish reading. So, a contiguous view that moves along a sequence. The whole trick is to update what you know as the view shifts, never to rescan. The right grows the window and the left shrinks it back to the invariant. Each element enters once and leaves once, so the work is linear. Name the invariant. Update, never rescan. Want to keep learning? Come find us at academy.rudewrite.com.